I'm pleased to introduce Dr. Norman Holden of the National Nuclear Data Center, Brookhaven National Lab, New York. Dr. Holden is the science co-chair with Dr. Peter Mahaffey, the education co-chair, of the IUPAC project on the electronic interactive periodic table, the elements and isotopes. Dr. Holden?
I hope you're all enjoying Malaysia. Thank you for inviting me to this international conference. I'm just sorry that I couldn't be there in person, but I would still like to share my thoughts on the history, the rationale, and the scientific data that underlies this project. It's a joint collaboration between scientists and educators to generate a tool to help in the understanding of science. Atomic weights were first introduced at the start of the 19th century by John Dalton, and chemical methods were used for the measurements. Isotopes were first introduced by Frederick Soddy and first measured by Francis Aston in the early 20th century. By the 1950s, the measurements of isotopes provided better atomic weight values and uncertainties than those from traditional chemical methods. In nature, chemical, physical, and biological processes are mass dependent. As a result of this mass dependency, there are changes in the isotopic composition for many chemical elements. The uncertainties in atomic weight values are a combination of measurement uncertainties plus these natural variations. With the improvement in measurement instrumentation, the uncertainties from measurements decreased significantly to the point where for many elements the natural variation exceeded the measurement uncertainties. To address this situation, the Commission on Atomic Weights introduced the concept of atomic weight intervals. These would provide an upper and a lower bound for the atomic weight and their measurement uncertainty and natural variations. How do you explain intervals to non-experts? A group of scientists from the Inorganic Chemistry Division pondered that question. Etienne Roth, in 2007, from the CEA in Saclay, hosted a meeting at the International Bureau of Weights and Measures, at which John DeLeta from Curtin University in Australia suggested that educational outreach projects should be proposed to IUPAC, which would introduce the concept of isotopes and discuss the importance of isotopes in our everyday life. J.K. Bulkey from the U.S. Geological Survey in Virginia suggested that we use the periodic table as a framework for this introduction of isotopes. A project was submitted to IUPAC from the Inorganic Chemistry Division and the Committee on Chemistry Education, CCE. The projects committee insisted that a paper project with this data be completed before they would fund an electronic version of the periodic table. It has taken 9 years to collect all of the data, particularly for the applications of isotopes in all of the elements. But during this time period, there have been innovations in computerization that have led to the establishment of electronic apps, and we've taken advantage of that to produce many electronic apps to be used with our electronic periodic table. Ty Copeland from the USGS is secretary for the project. He created the colorful pie charts, and he arranged for additional funding from USGS that enabled us to complete the paper project. Other members of the team, Lauren Tarbach from USGS, who generated the computer file for the data. The scientific information was provided by Michael Weiser, University of Calgary in Canada, Thomas Walczak from National University of Singapore, Sinjay Yunita from the Science Museum in Tokyo, Glenda O'Connor and Dorothy Tepper from the USGS. Peter Mahaffey served as liaison with CCE and with the King's Center for the Visualization of Science. Do we have any science fiction fans in our audience? If we do, you're going to be disappointed with our periodic table. We do discuss xenology. However, we're not talking about the biology and culture of extraterrestrial aliens. We're talking about xenons isotopic abundance variations, which are used as traces to study the geodynamics of the Earth. Our 21st century periodic table provides relative atomic masses and isotopic abundances for stable and quasi-stable or long-lived isotopes, which contribute to the atomic weight measurements. All isotopes are included within our table. This would be stable as well as radioactive isotopes, and for those we also supply 3 half-life ranges. As far as applications to our everyday life, isotopes are listed in 7 different categories. Those categories are biology, earth and planetary science, forensic science and anthropology, geochronology, industry, medicine, and the generation of radioactive isotopes. We have a total of 441 applications. An example of some of these for radioactive isotopes are in medicine. We discuss X-rays, CAT scans, MRI diagnoses, and stress tests. And in industry, the use in smoke and radiation detectors and determining flaws in metal parts. For the stable isotopes, in forensic science, they're used to determine the adulteration of food and drink. They trace the history and origin of pollutants, or they can be used to determine the source of toxic elements in the body. To provide understanding of a lot of this material, we define or explain 150 terms in our text and an additional 200 terms in a glossary. The total number of isotopes that we include in the table, there are 253 stable isotopes, 36 quasi-stable isotopes, but 3,001 radioactive isotopes. We're very excited about this collaboration between scientists and educators in the generation of this tool, and we hope you as educators will spread the word internationally so that users and others of this tool will have a better understanding of science. Thank you for your time.